Welcome to this video lecture. My name is Professor Cody Powell. We are continuing with our series. My class is called The Fundamentals of Smart Systems. Specifically, we've been talking about in this module simulating dynamic systems with Simulink. We are going to continue showing some of the complexity and the nuance of Simulink and showing just how powerful it is in doing various tasks. In this video, we're going to talk about uh, incorporating equations that have derivative calculations that are dependent on the state itself. So for example, in the last video, we calculated our differential equation, which gave us dv dt, or the change in volume with time. We integrated that dv dt signal to get volume. So I'm going to show you today is what happens if our differential equation depends on volume itself. So it's kind of a chicken and egg situation where to calculate dv dt, we need volume. To calculate volume, we need dv dt. So I'm going to show you how to do those kind of calculations in Simulink. Additionally, I'm going to show you how to incorporate intermediate equations that may be necessary for solving the differential equations themselves, or sometimes you just want to calculate extra information to use in the analysis of your system. And so you can do those kind of things with more customization in Simulink. In our last video lecture, we showed this simple tank system where we have a tank, we have fluid flow coming into our tank, that's Q in. We have fluid flow leaving our tank, that's Q out. And of course, the flow in and the flow out affect how much volume of liquid is in our tank. So we did this simple differential equation based on a material balance that says dv dt, or the change of volume with time, is equal to the flow in minus the flow out. So we're going to suppose that, let's suppose that we can no longer control this valve. We can no longer control Q out directly. Rather, let's suppose that Q out is some kind of function of height, where the height is the height of the liquid level in the tank. So hopefully this makes sense physically to you, that the more liquid you have in a system, and the higher that height is at the top of the fluid level, the more gravitational force you have pushing down and ultimately pushing fluid out of your system. So you've seen this in your bathtub or in a sink or in whatever, that flow coming out of a system can very much depend on height. So in this case, our height is a function of our volume. Specifically, our volume is equal to the cross-sectional area of our tank multiplied by the height. And if we rearrange that equation, we get that our height is equal to our volume divided by the cross-sectional area. So we're going to have to introduce an intermediate calculation like this into our system, which will be very easy for Simulink to handle. Once we've calculated the height, we can actually calculate Q out as a function of that height. Specifically, we're going to introduce a new variable called the valve constant, and we're going to say that Q out is proportional to this constant multiplied by the square root of the height. So still we'll see that the higher the level in the tank gets, the higher our Q out, or our flow out of the tank, will be. Just by way of introducing some numbers, so we have different ranges defined for the variables, but let's look carefully down here where we're given the physical diameter of our tank is going to be 4 meters. So 4 meters in diameter. We're given this value for C, that it is equal to 3.2 meters to the 2.5 power per minute. And if you went back to our equation, if this has units of meters to the 2.5 per minute, H has units of meters. So when you take the square root of that, you get meters to the 0.5 power. So the end result of this is that you still get units of meters cubed per minute here for Q out. All right, so we've introduced some of the basics, including these intermediate equations. Let's go back to Simulink now and implement these into our model. So last time we were left with this model that just had that simple differential equation that dv dt equals Q in minus Q out. So let's give it some more information. When we use a percent sign here in MATLAB or Simulink, that basically lets us add in comments into our code. So whatever comes after the percent sign does not impact the code whatsoever, but it allows us to give ourselves little comments to help us with better organization. So we need to define some constants. So we had C was equal to 3.2 This is our valve constant with units of meters to the 2.5 per minute. We also have our diameter is equal to 4. So this is the tank diameter with units of meters. We can calculate an intermediate now. So our cross-sectional area is going to be pi fourths times our diameter squared. I'm going to cut the commenting for a little bit just because I want to keep the video a little shorter. All right, if we know our cross-sectional area, we can now calculate h as an intermediate. So here we have h is equal to our volume divided by our cross-sectional area. So there's a problem here, and that is volume. We don't have volume coming in as an input to our system. So that can be problematic. So what I'm going to do, we're actually no longer going to be able to specify Q out. So I'm going to change Q out to be volume. Our system will no longer, or this function will no longer take Q out as an input. Rather, it'll take the system volume as an input. So if I have my function receiving volume as an input from another signal in Simulink, then I can calculate that volume here. So notice our volume balance will remain the same. It's still going to be the change in volume with time is equal to Q in minus Q out. However, we no longer know what Q out is, at least in terms of the code we've written so far. So here we can change Q out. Rather than being an input, now we're going to make it an intermediate. And we're just going to use that equation that we just defined, that Q out is equal to C times the square root of H. And I'm going to comment that out with a semicolon. That's just to suppress Simulink and MATLAB from printing this out at every time step. Okay, so now we have rearranged our model a little bit. It's actually a different model because we no longer control the outflow in this case. Rather, outflow is a function of the height in the tank, making this a gravity-drained tank. So when I go back out to my model, and again I just do that by clicking here to go back to the main simulation, I no longer have Q out as a source, but I need to define volume coming in. So this is where I was talking about our equation is dependent on the state. So we need to calculate dV dt, and ultimately dV dt is a function of volume. So it is this chicken and egg thing. And the way that we can do that is by taking this signal and looping it back to a place where we know that the volume signal or the volume information will be available. And this is instructive to tell us a little bit about how Simulink works. It uses what's called a sequential modular pattern for solving differential equations. So the flow of information would go something like this. Information comes from our source blocks. It goes into this block, this MATLAB function, which calculates the derivative. That derivative flows into here, and we had to give volume an initial condition, if you remember. So we started out with an initial volume of 10 meters cubed. So initially, Simulink is going to take that initial condition and use that initial condition to calculate the derivative. And then over time, you'll see we calculate the derivative, we integrate that derivative to create the state variable v, we loop that state variable back, calculate the derivative again, and Simulink keeps integrating in this recurrent kind of way. So that's the sequential modular pattern. So let's see what happens to our tank now when it becomes a gravity-drained tank rather than a system where we can control the inflow and the outflow independently. So we clicked solve, we're running the simulation for 100 minutes. Let's take a look at what happens. So when we analyze what's happening here, we see our tank goes from this initial volume of 10 meters cubed. We're keeping our inflow constant, so that 10 eventually levels off to a steady state at this value of, if I zoom in here, I can get a little closer to the value of about 7.67 cubic meters. So this is all great. Unfortunately, at this point, we don't actually know what the outflow is or what the tank height is, and there's a simple way to remedy that. We're already calculating height and we're calculating outflow. So what we can do is we can create more inputs or more outputs here from our model and just say we create this vector of outputs. So we're just telling our function, hey, we also want to know what the value of h is and what the value of q out are. So this function can churn out more things besides just derivatives. So if we added some more scopes here, I'm going to take this scope to plot my height. I'm going to create another scope to get both of my flow rates. So I can go in here and go to this block parameters. That if I go up to the scope and go to number of input ports and change that to 2, I find it useful to plot similar variables on the same plot. So we can use this first slot to plot our inflow, and we can use this second slot to plot our outflow. And what you should see is that eventually, when you reach steady state, because the volume is no longer changing, that Q in and Q out should become the same. So let's see how that plays out. We'll go here. When I click on my scope and go to this block with all the 4 arrows pointing outward, that lets me zoom out. And we do see that our outflow is initially 2.85 because it has that higher height to push more fluid through, but ultimately we reach this steady state where our inflow equals our outflow. And of course we can do things like simulate scenarios where the flow into our system is variable, do the integration. Simulink is just awesome with running all kinds of different scenarios.